Hello everyone. My name is Keshav Mishra and this is my graduate literature survey project for CSC 755, Software Testing and Quality Assurance. My topic was Human AI Collaboration in Software Engineering and Quality Assurance, Trust, Productivity, and the Proxy Metric Gap, cases where the number we measure and the thing we actually care about quietly drift apart. Over the next 25 minutes, I'll walk through the literature, the taxonomy I built from it, and where I think the field should go next. So here's the roadmap. I'll start with why human AI collaboration in software engineering and QA matters right now, and the 4 research questions that shaped this survey. Then I'll introduce a taxonomy I built to organize the 13 sources I reviewed, followed by the comparative findings that came out of putting those sources side by side, including 2 places where the literature seems to disagree with itself. From there, I'll go deeper on 4 representative papers, talk through practical implications and open challenges, and close with lessons learned, including a candid look at how I used AI tools while producing this survey and where I had to catch and correct it. Let's start with motivation. Why this is fundamentally a quality assurance problem and the 4 research questions I built the rest of the survey around. Let's ground this in why it matters. Large language models have moved from research demos to daily tooling. GitHub Copilot autocompletes code in line. ChatGPT drafts test cases and explains errors. And internal assistants like Google's Bard are being piloted for things like developer certification exams. This isn't speculative. Tanzil and colleagues' 2024 ICSC survey found that 98.52% of the software engineers they surveyed had already used ChatGPT for some part of their work. What makes this a QA problem specifically is that it breaks an assumption QA has relied on for decades, that a test either passes or fails, and running it again gives you the same result. Generative AI disrupts that twice over. First, the AI itself is now a QA subject. An increasing share of the software under test is a model whose outputs are probabilistic, so the usual pass or fail oracle doesn't apply cleanly. Second, the AI is a QA collaborator. It's now generating the tests, the code reviews, and the documentation that QA processes used to assume were entirely human authored. So verifying AI output isn't a side concern anymore. It's becoming a core software engineering and QA task in its own right, which is exactly the space the survey sits in. These 4 questions organized everything that follows. Research question 1 asks whether AI-assisted testing tools, automated test generation, LLM output, and correctness detection actually meet the reliability bar practitioners set for them, and specifically whether a commonly reported metric like code coverage tracks a metric that actually matters, like whether the test catches a real bug. Research question 2 asks how the productivity gain from AI coding assistants, measured empirically, differs between controlled lab settings and real workplaces, and if it differs, why. Research question 3 is about trust. How is trust in an AI collaborator calibrated or miscalibrated across novice and expert users, and what that means for how these tools should be designed? And research question 4 asks what responsible use and governance principles are actually emerging for generative AI in software engineering, and how consistently they're applied or even disclosed. 2 of these, research question 1 and 2, turned out to have genuine documented contradictions in the literature, which I'll walk through shortly. Before the findings, a quick word on what I reviewed and how I organized it. 13 sources and an original taxonomy for making sense of them. The corpus spans 13 sources published between 2023 and 2025. 5 sit in venues most software engineers would immediately recognize: IEEE software, the ICSC research track, ISSTA, IEEE transactions on software engineering, and the FSC companion proceedings. 2 sit in venues that are easy to mix up with better known namesakes. One paper is in a Springer journal that shares the name with a well-known conference, but isn't it? And another is in a workshop that's co-located with, but distinct from, its main conference. I flagged both explicitly rather than quietly counting them as confirmed. The remaining 6 come from adjacent software engineering, human-computer interaction, and AI venues, and one, a set of field experiments on GitHub Copilot, is a non-peer-reviewed economics working paper that I decided to keep anyway, because it's the only large-scale, multi-company field experiment on AI-assisted productivity in the whole set, and that kind of evidence is rare to find. This is the taxonomy that I came up with. It's not adapted from either of the 2 other surveys in this corpus. The horizontal axis groups papers by the primary software engineering or quality assurance activity they address: test generation and verification, AI output correctness and review, developer productivity and workflow adoption, trust and explainability, and strategic or ethical framing. The vertical axis orders papers by evidentially rigor: position and vision pieces with no original data at the bottom, working up through small qualitative studies, controlled studies and surveys, up to large-scale empirical studies and systematic reviews at the top. And the color of each chip encodes venue confirmation status, which ties this diagram directly back to the venue analysis I just walked through. The point of building it this way is navigation. If you wanted only the highest trigger evidence on productivity, you'd go straight to the top row, developer productivity column, and land on the field experiment paper. If you wanted position level framing on testing, you'd find it in the bottom row instead. You don't have to read all 13 papers to know where to start. 3 things jump out once the grid is built. First, rigor really does increase toward the top. The 2 systematic reviews and the only large-scale field experiment in the whole corpus all land in that top row, while the bottom row is exclusively non-empirical framing work. Second, and this turns out to matter a lot later in the talk, 2 columns are almost empty: AI output correctness and review, and developer productivity workflow adoption specifically. Each contain exactly 1 paper. That's despite both of those activities being central to the whole topic. I want to be clear that this is a genuine gap in the literature, not a side effect of how the search was conducted. These topics weren't avoided, they're just thin. Third, the papers in confirmed major software engineering venues cluster heavily in the test generation column, while the trust and explainability work is concentrated in venues outside that major venue list. That suggests the flagship software engineering venues have, so far, engaged more with the mechanics of AI-assisted testing than with the human side of trusting it. And now the comparative analysis. What these 13 papers say about testing automation and about trust and productivity, including 2 places where they seem to disagree. This is the heart of the testing automation findings. And the pattern that keeps repeating is: things that look good on an easy metric look much less good on a harder one. Lopes and colleagues' AG1 test tool found that GPT-4 generated Java tests matched or beat human written tests on ordinary code coverage. But every single configuration they tried underperformed humans on mutation coverage, which is a much better proxy for whether a test actually catches a bug. Best case for the AI was 0.54. Humans hit 0.69. Wang and colleagues' systematic review of 102 studies shows the same pattern at a much larger scale. LLM-generated test coverage on SF110, which is a large, realistic benchmark, was just 2% line coverage and 1% branch coverage, compared to 87% line coverage on human eval, which is a much simpler toy-style benchmark. That's not a small discrepancy. It tells you the benchmark you pick can completely change how good these tools look. And practitioners seem to sense this. You and colleagues found that most published test generation techniques satisfy at most 47% of practitioners' expectations on correctness and bug detection in complex, real-world scenarios. And Tanzil and colleagues found that only 0.74% of surveyed practitioners fully trust ChatGPT's output without double-checking it themselves. Here's the first contradiction I found. It's a good example of the kind of comparison the survey is meant to make. On the left, Lopes and colleagues ran a controlled comparison and found LLM-generated tests roughly matching human-written tests on coverage, but clearly behind on mutation coverage, the metric that actually reflects whether a test catches an injected bug. On the right, Wang and colleagues' review reports something that looks, on its face, like a much worse result. 2% line coverage on the SF110 benchmark. Read side by side, these look like they disagree about how good LLM-generated tests really are. I don't think they do disagree. I think they're measuring different things. SF110 is made up of real, large, structurally messy open source projects. Lopes and colleagues' dataset was explicitly pre-filtered for compilability, which biases it toward well-structured code. The authors say so themselves. So the honest reading is that LLM test generation performance is highly sensitive to how complex and messy the target code is, not that there's a real disagreement about what these models can do. On the human side, a few patterns recur across very different study designs. Kien and Wexler ran a within-subject study of 76 professional engineers completing a coding standards exam with and without access to Google Bard. Novices gained significantly on open-ended questions when they had AI access. Experts showed no significant gain at all. And here's the twist. Experts distrusted the AI more than novices did, and were correspondingly less likely to use it to correct their own mistakes, which the authors describe as experts distrusting, quote, imperfectly in a way that can actually punish their performance. Hamza and colleagues' hands-on workshop with professional engineers captured the same tension qualitatively in a line I think is worth quoting directly. Trust but verify. GPT can propose, but only a developer's eye can truly diagnose and resolve. And Wrong and colleagues' review of explainable AI research found something sobering at the meta level. Only about 20% of XAI evaluation projects even involve human subjects. And of the ones that do, roughly half find no clear benefit from the explanations at all. The second contradiction is about magnitude, and it's actually the authors of the field study who flag it themselves. which I think is a model of honest reporting. QA and colleagues ran three genuine randomized field experiments, not lab tasks, real production work, across Microsoft, Accenture, and a third anonymous company for a combined 4,867 developers, using actual GitHub telemetry over months. Their headline result is a 26.08% increase in weekly completed pull requests among developers who adopted Copilot. Compare that to Peng and colleagues' earlier lab study, cited within the same paper, which found a 55.8 to 58% reduction in time to complete a single controlled coding task. QE and colleagues note this gap themselves rather than letting a reader stumble onto it, and their explanation is that these numbers are measuring different things. Completion time on one narrow, Copilot-friendly task in a lab versus completed task throughput across the full, messy mix of real production work, where plenty of tasks aren't the kind Copilot is good at. So again, not a real contradiction about whether Copilot helps, more a lesson about how much the setting and the outcome measure the shape, the number you get. I would like to now dive into four papers that, between them, cover testing automation, large-scale productivity, individual trust, and the meta-level view of the whole field. The first paper is Wang and colleagues' 2024 review in IEEE transactions on software engineering. I picked it up because it functions almost like a second, higher altitude version of this survey, a systematic review of 102 primary studies on LLMs in software testing, with a genuinely rigorous protocol. Explicit search strings across multiple databases, clear inclusion and exclusion criteria, two independent raters with the tiebreaker, and a public GitHub repository that keeps the full list of reviewed papers maintained and updated. The finding I keep coming back to is their caution about data leakage. They point out that popular program repair benchmarks are probably contained in the data these models were pre-trained on, which means some of the eye-popping repair numbers reported elsewhere in the literature may not reflect real generalization at all. They also found zero studies applying LLMs to early lifecycle testing work, like requirements analysis or test planning, a gap that lines up exactly with what my own taxonomy shows. Second is QE and colleagues' field experiment paper on GitHub Copilot. This is a working paper, not a peer-reviewed publication. It's economics research and not software engineering, but it was interesting to keep in the corpus because of its scale and realism. 3 actual randomized control trials were run as ordinary business decisions inside real companies, covering 4,867 developers using two-stage least squares regression to handle the fact that not everyone who was given Copilot actually used it. The headline number is a 26.08% increase in weekly completed pull requests among developers who adopted the tool, with gains directionally larger for less experienced developers, and no evidence that code quality suffered as a side effect. Which matters, because a productivity gain that comes at the cost of quality wouldn't really be a QA-friendly result at all. Third is Kian and Wexler's study, which I think is the most methodologically careful look at trust in the whole corpus. 76 professional software engineers each took a 10-question company internal Java certification exam with randomized access to Google Bard versus traditional resources. What makes it rigorous is that they didn't just ask people how much they trusted the AI. They paired a validated psychometric trust scale given before and after the task with actually observed behavior. Did people use the AI, skip it, or use it to fix a mistake? That combination is what surfaces the finding in this quote. Experts distrust the AI and distrust it imperfectly, meaning they're more likely to reject it even when it's right, which can actually hurt their own performance. It's a nice illustration of why calibrated trust, not just more trust or less trust, is the right design target. Fourth and last is Lobs and colleagues' AG1 test paper. They built a pipeline that combines Jacoco for coverage, PyTest for mutation testing, and TS-Detect for test smell detection, and a new dataset called Classes to Test with over 147,000 test classes to compare LLM-generated Java tests against human-written ones. The coverage versus mutation gap I mentioned earlier comes directly from this paper, 0.54 versus 0.69. But the detail I think is most important, and the one that's easy to miss if you only look at headline number is that roughly 2/3 of the generated test classes were rejected outright, and most of those failures were basic import or syntax errors, not the AI finding some clever new bug. That's a meaningfully different story than AI writes weaker tests. It's closer to AI often doesn't finish the job at all. Let's close out with what this means in practice, what's still unresolved, and the research question I'll propose next. 5 things follow pretty directly from all this for anyone actually adopting these tools. First, don't trust coverage alone as a signal of test quality. Pair it with mutation testing, which is genuinely feasible. Lopes and colleagues already built that exact pipeline. Second, design for calibrated trust rather than more trust or less trust. Surface confidence signals, not just answers, especially since experts and novices misjudge these tools in opposite directions. Third, keep humans deliberately in the loop at the points this literature keeps flagging as AI weak. Security review and complex logic debugging. Fourth, disclosed and verified AI use is actually achievable. Freeman, Robert, and Washington's own paper was AI drafted and then human revised, with an explicit disclosure, which is a workable model. And fifth, feed these tools the way practitioners actually work. Most published techniques generate tests from code, but most practitioners write tests from requirements descriptions first. 4 open challenges kept surfacing. Benchmark realism and possible data contamination. Some benchmarks may already be inside these models' training data, which would inflate reported results. A recurring pattern where a proxy metric misleads. Coverage doesn't track mutation kill rate, and self-reported trust doesn't track demonstrated behavior. The same underlying problem showing up in 2 unrelated corners of this literature. LLM testing research is heavily concentrated in the middle of the testing lifecycle, with few studies on requirements analysis or integration and acceptance testing. And structurally, the 2 thinnest columns in my taxonomy, AI output correctness and review, and productivity from workflow adoption specifically, are exactly the 2 activities most central to this whole topic. This is the research question I propose, and it comes directly out of the gap the taxonomy exposes and the proxy metrics pattern I just described. Does pairing AI-generated test suites with automated mutation testing feedback instead of coverage-only feedback measurably improve real-world fault detection rates and practitioner trust in these tools? Nobody in this corpus answers that directly. Lopes and colleagues call for exactly this kind of mutation-aware test generation as future work, but they don't build or evaluate it. And no productivity or trust study here manipulates the feedback metric shown to developers as an actual experimental variable. That gap is, I think, the most actionable next step this literature points to. Just to go over some of the lessons I learned. The literature itself modeled good practice more than I expected going in. Authors flagging their own data leakage concerns, their own small samples, their own unresolved questions rather than only reporting successes. On the AIU side, tools were genuinely useful for mechanical synthesis, cross-referencing 13 papers into one consistent schema, and producing first-pass drafts in an unfamiliar format. But left unchecked, AI output defaults to a recognizable voice, hedged and prone to narrating its own process. And catching that took a full read-through, not just better prompting. The habit that mattered most was rendering every generated artifact and actually looking at it before trusting it. Thank you for watching. To sum up in one line, AI is already deeply embedded in software engineering and QA workflows. It helps most where its output is verified rather than trusted blindly. And the biggest opportunity is closing the gap between the metrics we report and the outcomes we actually care about. Thank you.